All right, hello pre-calc honors kids. This is Miss Lefort, and today we're looking at velocity. So velocity is speed and direction. So it tells us more than just speed would. So velocity is our rate of change of position. And speed is the absolute value of velocity, because speed doesn't take into consideration which direction it is going. So when we're looking at this graph here, notice on this first part, it is, whatever this is, it doesn't really tell us here, is speeding. You know, the speed is increasing. The velocity is increasing. The velocity is constant. The velocity is decreasing. Velocity is constant again. And then the velocity is decreasing. And then right here, it stops, okay? Right there, it is, the velocity is 0, okay? You see it there and you see it here. So velocity is 0. So what does that mean? It's actually where the particle or the person or whatever is turning around, okay? See, they stop for a second, and now they're speeding up in the opposite direction. And then here, they're slowing down back to 0, stopped and turned again, and then going back in the direction they were originally. Here we have our constant speed, and here they're slowing down again. So we're back to 0 at that point. So your velocity tells you more than just the speed. It tells you where it well, not where it is, but the direction it's going, okay? The position it is, which direction it's heading, right, left, up, down, that kind of thing. So if we were looking at velocity, speed, the absolute value of velocity, then the red part would stay the same, but this little blue piece would just kind of be flipped back over there, because we'd look at positive everything. We're just looking at how fast they're going, not really what direction. Okay, so now this next part is dimensional analysis. Sometimes I've heard it called the conversions, I think in the science classes. You need to be able to go from one unit to another. And most of this stuff, I believe, should be something that you should know as what we call common knowledge. So when we have 3 miles and we're going to inches, and then let's see, this would be 3 miles. And let's see, we multiply by some kind of conversion that equals 1. Well, I know, let's see, 1 mile is 5,280 feet. And 1 foot is 12 inches. So remember from your sciences, the miles would cancel, or those words would cancel. Here the units would cancel. Feet would cancel. So I'm left with inches, which is what I want. So that's how you know how to set that thing up. So then you grab your calculator, and I think you get 190,080. So that would be the answer to how many inches 3 miles would be. And it makes sense, because that's a lot of inches. On this next one, we have 45 kilometers per hour. So 45 kilometers per hour. And we need meters per second. So let's see, how many meters are in a kilometer? Well, 1 kilometer or kilometer is 1,000 meters. So think a kilo means 1,000. I'm expecting that you know that. Then hours to seconds, well, let's see, 1 hour has 60 minutes, and then 1 minute has 60 seconds. Now, you can combine that. I know in class a lot of people did, and that's totally fine. Let's see, the unit kilometer cancels, the unit hour cancels, minute cancels. So I'm left with meters per second, which is exactly what I need. And if we take our calculator out and calculate all of that, you get, let's see, what is that? 12.5 meters per second. All right, so let's look at the same thing, but dealing with circles, okay? So we're going to combine it a little bit what we were learning earlier in the last lesson. Okay, here's our circle. A revolution is 1 trip around the circle. So if we have 7 revolutions every 3 minutes, and we want to go to radians per second. So let's see, I know that 1 revolution is 2 pi radians. It's 1 trip around the circle. So, and then per second, minutes to second, 1 minute is 60 seconds. So then that means these, let's see, revolutions cancels, minute cancels, and I'm left with radians per second, which is what I need. So if I multiply this out, that gives me 14 pi over 180 radians per second, but that simplifies to 7 pi over 90 radians per second. Now this is exact, right? I mean, we could get a decimal if we put that in the calculator, but for now we're going to leave everything exact unless they tell us we need to change it, basically. All right, so here we have a horse making 3 revolutions every minute. So this is, he's like in a stable. He's on a little post here, and he's going round and round this circle. So we want to know the angular velocity of this horse and the linear velocity. So the formulas for this, and you will have to know these, okay? Angular velocity is W equal to theta over t. Okay, that's a fancy W. It's lowercase. It's got a little twirl out to the side. Then, of course, theta, which isn't got to be in radians again, and t is time. Linear velocity is a V, but it's kind of a fancy V. This is R times theta, one way to look at it. So, I mean, the W there, or we have R theta over t. Either one of those work because, you know, the W is just theta over t, so I can insert either one that I want. So you're going to just need to know these, okay? So I'm going to say no because you do need to know the formulas. Now, if we look at it in this particular example, we had this horse and we want angular velocity. So the first thing I want to do is find that. Angular velocity, let's see, he's doing 3 revolutions every minute. So this would be 3 revolutions, which is 2 pi, right, for the radians, every 1 minute. So this would be 6 pi, and that is in radians per minute. So that would be the angular velocity. Now, the only difference from that to go to the linear velocity is you're dealing with r. You see how that's the only thing that's different? I'm going to take that and multiply by r. So my linear velocity would be 15 meters times 6 pi, and that gives me, what is that, 90 pi, and this would be meters per minute. So anytime it's linear, you're going to have a linear measurement up in here. So just be careful with that. It's very easy to get the units mixed up on those. So on this page, we have here at the top, in this little corner, is a little shortcut. If you happen to know revolutions, they tell us what it is, then all you got to do is multiply that by 2 pi to get to the angular velocity. And then go from angular velocity to the linear velocity, all you got to do is multiply by the radius. So if you're going backwards from linear velocity to angular, you divide by r. And here, to go from angular velocity to revolutions, you would divide by 2 pi. So notice you're either multiplying or dividing by, that depending which direction you're going. So that kind of is a little shortcut here to kind of help you out, help you remember it. So if we're looking at this ceiling fan, here we have the ceiling fan, 9 revolutions per minute, and a radius is 3 feet. If I wanted to find the angular speed, that would be, let's see, 9 revolutions, so 9 times 2 pi, because we need it in radians, divided by 1 minute, so that is 18 pi radians per minute. If I wanted to go to the linear velocity, I have to use this radius, so this would be 3 times the angular velocity. So that gives me 54 pi, and this is feet per minute. because it has the same units as the radius. All right, so let's look at the next little one. We have 5 revolutions every minute. So this is going to be a carousel. I'm not sure if I'm spelling this right, but here we have a carousel, and I'm going to just draw this little thing up, okay? Let's say this is 12 feet, okay, in radius. And it is doing 5 revolutions every minute. We want the linear velocity, but they're going to, of course, throw a wrench in it because they're saying, hey, put it in miles per hour. Yeah, I know, right? Okay, so first of all, we would say, okay, a linear velocity, the radius is 12 feet, and then our angle would be 5 revolutions, so 5 trips around the circle, so 5 2 pi's every 1 minute, okay? So this would be, that would be 120 pi, and this would be feet per minute. So we have it, but we don't have it in the right form. They want miles per hour. So 120 pi feet in 1 minute. And we need to get to miles. So what, 5,280 feet in 1 mile. All right, that got me to the miles. Now I need hours. So 1 minute. So let's see, minutes. There's 60 minutes in 1 hour. All right, so then feet cancels, minute cancels, and I'm left with miles per hour, which is what I need. So if I multiply all that out, and this time I'm going to go to a decimal because it makes more sense when we talk about miles per hour. Nowhere on your car speedometer thing does it show you pi's, right? So let's do 4.28 miles per hour, which makes sense. They're going pretty, not real fast, you know. So it feels like it's faster probably if you're on the thing. Now, what if we had another person that was sitting on here? We're assuming this guy's out here on the edge, but what if we had another person on it that was a little bit more scared, right? So this person is in here, riding on the inside, probably on the bench, not even on one of those horses that goes up and down. So this one is traveling, the radius, it would be, I don't know, let's make this up. The radius would be, say, I don't know, 2 feet. Okay, so they're very small. They're into the middle area. So what would be the same for these two people? Would their linear velocity be the same or the angular velocity? Well, I'm hoping you notice that it is the same angular velocity. Okay, because the thing's spinning, and that's not changing, how fast it's spinning, but what's changing about it is the distance that this is going around. Like this one's going around here, and the other's going around the whole outside. So obviously, the one outside is covering more distance, so that speed for the linear is going to be different. So sometimes the angular speed's the same, sometimes it's linear speed. It really depends on the problem. So I'm going to show you one of the other ones in just a bit. Alrighty, so let's look at the next question. A point on the rim of a wheel with a diameter of 2 yards has a linear speed of 100 feet per second. Find the angular speed in radians per second and the number of revolutions in a minute. Okay, so they got multiple things going on here. We got 2 parts of things that we need. So first we're going to look for our angular speed, and they want it in radians per second. All right, so here's our circle for the wheel. Diameter is 2 yards. And remember, diameter goes all the way across. Wait, I don't want the whole thing. I need the radius. So what's the radius? You're right, it is 1. But that's 1 yard. The issue is this is in feet. See how it's so easy to accidentally mess that up? This is feet per second. So I need them both to be in yards or both to be in feet. So I'm going to just change this 2 yards to 6 feet, right? Because there's 3 feet in every yard. So I'm going to say this is 3 feet and then not even worry about the other one. So my radius here is 3 feet. So my angular speed would be linear speed. Oh no, we don't know yet. It's got linear speed. Okay, so I gotta back up. I can't get that one straight ahead because we don't know that, but we do know that the linear speed is r times the angular speed. Linear speed, they're telling us, is 100. The radius is 3. So yeah, oh yeah, I can use that and figure it out. So this would be 100 over 3 radians per second is my angular speed. So this would be like an exact answer. All right, so the next part says the number of revolutions in a minute. Okay, number of revolutions. So how far does it go? Well, let's see. If the angular speed is 100 and the radius is 3, and we got our, well, no, we got our angular speed here is 100 over 3. How many revolutions is that? Well, if you remember, this would be theta over t, and theta just has to be in radians. So if I want to go from radians to, revolutions, I can just divide by 2 pi. So 100 over 3 radians. Oh, it needs minute anyway. Okay, radians per second. Okay, so I'm going to do this. And then we need it to be, let's see, 2 pi radians is 1 revolution. Okay, so I'll give this to the revolution. Seconds to a minute. There are 60 seconds in 1 minute. So then when we cancel these words, radian cancels, seconds cancels, I get revolutions per minute. Yay, that's exactly what I need. So, I think this is 318 revolutions per minute. So you can check that on the calculator and see if I'm right. Alrighty, we're making progress. Okay, here we have a bike that has a front wheel, the diameter of 40 centimeters, a back wheel with a diameter of 60 centimeters. Through what angle in radians does the front wheel turn if the back wheel turns through 15 radians? All right, so we have a front wheel that's smaller than the back wheel. Okay, so here's our back wheel. Here's our front wheel. I'm not real good at drawing bikes, so I'm not even going to kind of try, but not, it's awful. I know, that's not a bike. Anyway, so this one is, let's see, diameter is 60, so this radius would be 30. Here the diameter is 40, so this radius would be 20. And let's see, we want, what angle in radians does the front wheel turn if the back wheel turns through 15 radians? All right, so we know this back wheel is going 15 radians around, okay? 15 radians. It's weird that it doesn't have a pi with it, but that's okay. Well, I want you to think about this, okay? This is a bike on a road. So what is the same here? Would it be the same linear velocity or same angular velocity? Would these wheels be turning at the same angle speed or linear speed? It would be the same linear velocity. Because they're on a road. Think about it. They have to be going the same speed. You can't have half your bike going faster than the other half of your bike. It's got to be going the same. So the different thing here is your angular velocity. So it's different than that other example that we saw. So let's see. If we have the same linear velocity. So basically, I'm going to compare the back one. That's so weird how it all of a sudden made it really like super fat on my letters. Let me see if I can change that right quick to make it a little bit better. Okay, so we're going to look at the back one. And then we're going to look at the front, okay, and compare them. So the back, we know the linear speed would be 30 times 15 radians. Now, this is always in radians, so I don't need to say times 2 pi, okay? That's only if it was revolutions there or something. So here, this would be, let's see, that's 3 times 15 is 45, so 450 radians. And I know they have to be going the same. So on the front, then I know that this would be 450. The radius is 20 here. So if I divide that out, what does that give me? I think it's 22.5 That's our radians. Very good. Okay, so this is our answer. Alrighty, so last one. Yay. Okay, so we have a bicycle tire, circumference of 87 inches, and they give us an angular speed of radians per second. We want the linear speed. Oh no, they're changing our units to miles per hour. Okay, circumference is 87. So remember, circumference is 2 pi r. So we got 87 equal to 2 pi r. So r has to be 87 over 2 pi. Now, if you plug that in your calculator, you have to be very careful because a lot of them will give you an incorrect answer if you don't put parentheses right here, okay? Because it'll go 87 divided by 2 and then multiply it by pi unless you put the parentheses. So just kind of be careful and make sure you can get the right answer. But I got r equal to 13.486. So if they don't specify and we do use decimals, I'm going to want you to go 3 places after the decimal to avoid having any round off errors. All right, so now we know the radius. We got the angular speed. So linear speed is just the radius times the angular speed. So that's the one we're looking for. R is 13.486. Okay, 486. The angular speed, they told us, is 20 radians per second. So if we multiply that out, I get 276.930, and this would be inches per second. Okay, too bad that's not our answer, because it does look pretty. But they want miles per hour. So I got to convert again. Okay. No worries, I can do this, right? So let's see. This would be 276.930 inches over 1 second, okay? And I need to go to miles per hour. All right, so I know that there's 60 seconds in 1 minute. So I got rid of the seconds, okay? But I still need to get to hours, so 60 minutes in 1 hour. All right, so I got minutes canceled. Now the next one, inches. Inches. There's 12 inches in 1 foot. Okay, so my inches cancel now. And then to get feet to cancel, there's 5,280 feet in 1 mile. That gets me to the mile. So my feet cancels. Where's feet? There we are. All right, so if I multiply all that out and get an answer, it gives me 15.735 miles per hour. And think about it, if you're on a bike and traveling 15 miles an hour, that's pretty good. You're making good time. That's awesome. Sounds about right. All righty, so enjoy working the problems. Come see me if you have questions.